And here we go. We pick up with the curve sketching piece right here, okay? So yesterday we looked at two curves. You had a pretty good idea of what they looked like. I want to give you an example of sketching a curve that you really don't know what it looks like. What can somebody tell me? Tell me something, anything intelligent about that curve as you look at it right now. Has an asymptote, doesn't exist at 1 or -1. So my guess is that we would have vertical asymptotes at x equals 1 and x equals -1. When we consider the horizontal asymptotes or the end behavior, we have to let the limit go to infinity. But beforehand, I'm going to think about the intercepts. Those are always a nice thing to do as well. It gives us extra data, extra points. So how do I determine the y-intercept? If you plug in 0 for x, you get 0 over -1, which is 0. The x-intercept happens when the function is equal to 0. Is a fraction equal to 0 when the top is 0 or when the bottom is 0? The top. So you see that we have a 0 on the top as well. So just like the last one, this one goes through the origin as well. So let's think about the end behavior. I'm going to take the limit as this goes to infinity. 2x squared over, what would I factor out of the bottom? X squared, and you get 1 minus. Okay, great. So as you can see, this is going to go away. The x squareds cancel. You're going to be left with 2. It would appear that the horizontal asymptote should be 2, but let's let the limit go to positive infinity and a negative infinity. The limit as x goes towards positive infinity, the limit as x goes towards negative infinity of the function. So look at your original function. What do you notice about the top? It's always positive. And if you plug in a large positive number to the bottom and square it and subtract 1, it's still going to be positive. So positive over positive will give you, so this will go to positive 2. We saw the limit here was 2. Now let's consider the negative. So we go to negative infinity, the top will be positive. How about the bottom? Still positive. So it should have a horizontal asymptote of 2. The end behavior in this situation, we get a definite result, has horizontal asymptote of y is equal to 2. So we've got some information to give us a little bit of idea what the shape looks like. But what do I do in order to find intervals of increasing and decreasing, local min and local max? Derivative. Oh boy, what rule? Quotient rule. No easy way through this one, folks. We'll see how good our algebra really is. What's the derivative of the top? 4x times x squared minus 1 minus 2x times 2x squared all over x squared minus 1 quantity squared. Let's see what we have. In the top, you're going to get 4x cubed minus 4x minus 4x cubed. So you just get negative 4x over x squared minus 1 quantity squared. The bottom is always positive. Is the top always positive? Is it always negative? It's not always negative, is it? So we're going to have to, kind of consider some points here. Where is the bottom equal to 0? Negative 1 and 1. Where's the top equal to 0? 0. So let's plug in some values and see what happens. What's a value to the left of negative 1? Now we don't need to plug in the bottom because the bottom will always be positive. If you plug in a -2, the top will be positive. Plug in -1/2, the top will be positive. Plug in 1/2, it will be negative. Plug in 2, it will be negative. What does that tell me? Somebody tell me something. What does that tell me? Increasing from to -1, union with -1 to 0. Why did I not include -1? It's undefined at -1. Very good. When is it decreasing? 0 to 1, union with 1 to infinity. What other information can I glean from this other than the intervals of increasing and decreasing? Local max and local min. Local max and local min occur when it changes sign. Where does it change sign? 0. Is 0 part of the original domain? Yeah, it is. Yep. It's part of the domain. 1 and -1 are not. So it's part of the original domain. So is it a local min or a local max? Why? Changes from positive to negative. Very good. So local max occurs at 0. And when we plug it in, we get 0. We already know that one. So is there a local min? Why not? Doesn't change from negative to positive. Very good. Excellent. How do I determine the other two? Second derivative. Oh boy. This is ugly. Second derivative. Chain rule and product or and quotient rule, right? What's the derivative of the top? Times x squared minus 1 squared minus the top, right? So plus 4x times the derivative of the bottom. How do I do the derivative of the bottom? Chain rule. I got 4x times x squared minus 1. Is that where you guys are at as well? So times 4x times x squared minus 1 all over what? To the fourth. Anybody see something that will cancel? An x squared minus 1. If I factor that out of the top, I can cancel 1 in the denominator, correct? So that would make 3 left in the denominator, and I would factor 1 out of the top. Let's see what we have left. F double prime of x is, looks like I have a negative 4x squared. I have a positive 4. And then I have a plus what? 16x squared over x squared minus 1 cubed. So what's the top now? 12x squared plus 4 all over. Okay. What do you notice about the top? You can take out a 4, but I don't need to. Why? The top is always positive. You see that? If you just think of the graph of the top, it's 12x squared plus 4. It's going to look like that, right? It's always positive. So it's never equal to 0, is it? Where's the denominator 0? So that's all I need to test. The top is always positive. What would you like to plug in for the left of -1? I plug in -2, and I get Positive 4 minus 1 is 3 squared, so I will get a positive value. Now what would you like to plug in? 0. I plug in 0, and you get negative 1. That will be negative. Then you plug in 2, and we're going to get positive. What does that tell us about our result? Concave up from? Where is it concave down? Inflection happens where it changes sign. Does it change sign? It does. But are those points where it changes sign, are those part of our original domain? So therefore, there's no point of inflection. We are ready to sketch the graph. Notice you don't really know what the graph looks like until we start to lay it out here. I'm going to make a 5 by 5 graph. This is the most exciting part, because we're going to take out our calculator then and see how close we are. We want to take a wager. Want to wager a donut? I don't want to brag, but I gave away a bunch of donuts this morning in my second hour. I had somebody third hour offer me $10 for a donut. I accepted it. Yeah, I agree. Well, gee, $10 for a donut. Like, well, I'm really hungry. I'm like, I'm not $10 hungry, but whatever. Vertical asymptotes. I have a horizontal asymptote at 2. This is my structure. What point can I plot? Only one point on the graph I know. It is 0, 0. I wonder, between -1 and 1, what's the shape of the graph? Is it concave up? Is it concave down? Yeah, it says that it increases, then decreases. It says it's concave down, and it says that this is a local max. So following that information, I should be able to draw a graph pretty confidently that looks like that. That should match with everything else I have. How about the graph? Does it start out as increasing or decreasing? Increasing. Does it start out as concave up or concave down? Concave up. So it looks like it needs to look like that. Now, does it end concave up or concave down? Concave up. Is it increasing or decreasing? So I'm going to draw a decreasing concave up, which is like this. I sketched it. This is the best part. I go to my calculator. I should have a Christmas background now, shouldn't I? Turn my calculator on. Y equals, what do we got? I can't remember. 2x squared? Divide by x squared minus 1? I go to my window. I'm going to set it by a 5 by 5, we said. And I really hope that it's somewhat close. You know, all we can do is just do our best and try and, you know. Because I knew that the asymptotes were 1 and 2. So I thought 5 would be enough to see everything. But we'll see. I made an educated guess. I'm nervous. Not well. It's close, but without a doubt, it's a little bit different, right? I think I was a little bit sharper on the turns than this one was, but you guys are pretty forgiving. So, you know, I think it's cool that we looked at something at the beginning. We had no idea what it looked like, but the calculus allows us to find the hidden behavior. And again, that's just think, folks. Back in the day, it's only been for the last, 30 years that we've used a graphic calculator. Before that, what did people do? That's all they could do. That's all they could do.